Yes, this sounds a bit theoretical, and it is. So it's probably a bit more theoretical than most other talks here, but never mind, what do you expect from a mathematician? So obviously this is a vast topic, and so therefore I shall concentrate on 5 subtopics. Since I have 45 minutes, that's 9 minutes per topic. So we have to rush even then. Anyway, if there's any questions, please let me know. So I'll talk about resilience and consensus. I'll talk about sorting. I'll talk about log-structured merge trees. I'll talk about hybrid logical clocks and about distributed assist transactions. Obviously, it is lunatic to try all this in one talk, so therefore I shall be content to just give you the idea of what the problem with this is and maybe how it is solved. Well, besides the last one. So we have 9 minutes per topic, so we better get started. Let me tell you about the first one. Obviously, the bottom line is to implement a distributed modern data store, you need computer science. Now, consensus. A modern data store, or indeed modern applications, are distributed. So you have different parts. And there's various reasons for that. One is scale out, obviously, but another reason is to be resilient. Computers break; they break every night, and so therefore you have to have a resilient application. Now, if it's distributed, then the different parts somehow have to agree on things, like, for example, copies of data or the state of the system or whatever. And that is the problem with consensus. So consensus in computer science is the art to achieve that different parts of the system agree on whatever as well as possible. Well, you would think that this is easy. You just send a network message over there and you say, well, they agree because you just copy over data. Well, that is true in the case that things are good. However, if your network has outages, your servers fail, your disks fail and might maybe come back in a corrupt way, bits flip, machines fail, racks fail, network splits happened, and you all know this is not a theoretical thing. This shit happens. Yeah. And under these conditions, consensus is a much harder problem. How can you keep consensus if your network is split in half? Well, you can't. That's what I mean by as well as possible. So, what can we do about this at all? Well, I haven't even talked about malicious attacks. This is just bad things happening on its own. The traditional approach to this is the Paxos consensus protocol from 1989 and 98, what you might have heard already. But there's also something newer, which is called Raft from 2013. Paxos is a challenge to understand, not let alone implement, because it's somehow complicated. Well, the inventor of Paxos, Leslie Lamport, argues that if you think about it, you cannot come up with anything else. That is to some extent true, but nevertheless it's complicated, it's hard to swallow, and it's even harder to implement. There's lots of variance, putting emphasis on this or that, performance tuning this or that, extending this or that. It's really a big mess. Raft, on the contrary, is designed to be understandable. It's not better in every way, but it's a lot better in the way that it can be understood. So therefore, my advice in this business, if you have to solve consensus or use stuff with consensus, you should do the following. Try to understand Paxos for a while, because the papers are well written, they are fun to read, and it's a good challenge, and it's fun. Don't implement it. Then, if you have prepared your mind with this complicated Paxos, then go away and read a Raft paper, which is a beauty. Because it's written to be understood, and also the protocol is really, really beautiful and, in comparison, rather simple. But don't implement it either. Rather, use some battle-tested implementation you trust. So use something which implements Raft, or indeed Paxos, if that is working, and use that for consensus. But there's one more advice which is even more important. Do not try to invent your own. I can tell you, I have tried and of course failed. Many people believe consensus is something simple. Why don't we do it like this? Don't. You see, this raft paper is actually the result of a PhD thesis in computer science with 250 pages. And the protocol in there is not only described well, it is proven to work. There's a machine-checked proof that this protocol works. As a mathematician, this is what you want to use. And then should you implement it, and I said don't, follow this paper and the PhD thesis to the letter. That is your Bible. You shall not deviate from it. Because if you deviate the slightest step, then the proof is void, and you don't want to do that. Okay, so that's the problem. That is the solution. And now I try something even more crazy. I try to explain to you what raft is and how it works in one slide. Cannot work, but here we go. What you do is you take an odd number of servers and let them play democracy. So the typical thing is 3 or 5. So let's think 3. You take 3 servers, you want them to agree on something. And to keep things simple, what they want to agree is just a log of events. It's an append-only data structure. You just want to agree on these log of events. That's all. Now, everything is replicated to everybody because we want to agree, we want to copy. And what they do is they elect a leader. So essentially, one of them says, please elect me, and the others say, so as long as network is good, I say, okay, we elect you, fine. You are the leader. This is now the leader. And if you want to append something to the replicated log, only the leader may append. So the leader appends to its log, and it replicates everything to the others. They confirm, I have it, and then it's committed. Simple as that. Now, the append doesn't count when the leader has said it's appended to my log. After all, the leader could fail in the next second. The consensus is reached if a majority of the servers have appended it to their log. So in case of 3, the commit has happened if 2 of them have appended it. Then there is no way back. Notice that the leader appends it to its log first. There's one replica which manages first to replicate. And at that point of time, nobody knows that it's committed. Because the leader doesn't know that the other guy has committed. And the other guy doesn't know whether the leader has died in the meantime. So nobody knows that it's committed, but yet the condition has come. That is what makes these things difficult. Anyway, if a majority has persisted it to persistent storage, that is the point of no return. Now, there's very smart logic, which I cannot explain in one slide, to ensure that there's a unique leader and that the thing recovers. For example, there are terms. So a leader is always elected for a term. And whenever somebody thinks, oh, the leader isn't there hasn't been something from the leader for a long time, then they can have a new election, but only for a higher term. And it's in one sense, it's quite straightforward. On the other hand, it's extremely clever, such that the proof actually works. It's a lot of fun. It's a lot of fun to implement. It's a lot of fun to follow this proof, and it is proven to work. So as long as you don't deviate from that protocol, it's going to work, provided the assumptions of the proof are given. Now, what one usually does, one takes this log of events as the changes of a key value store. So you implement a key value store on top of that, and every change has to go through this log, and as soon as everybody has applied it, the leader says, okay, this now counts this transaction, and the new values of the keys are like this transaction says. Right. The person who invented this, that's the author of the PhD thesis, Diego Ongoro, has... Yeah, the idea was that I can click on it and have it, but I've done it even easier. I've already opened it. So this is running a little applet. I have not written it. This was Diego's work. And this is something you can play with. So for example, here you have 4 servers. Nobody is a leader yet. This one runs out of patience and says, okay, I might as well become the leader. So what it does, it says, I want to be a leader. It sends out messages saying, please elect me for term 1. And so it goes. The others say, okay, you might be a good leader for term 1. Here we go. Now they work. And I think I can even do things like append to the log. I have to tell the leader. I can send a request. Now you see, this is appended to the log of server 3 as 3. And it's quickly replicated to the others. If I do this a few times, you see eventually it catches up. Now obviously I can do things like stop a machine. If I do a request, well, it's still fine. It's replicated to the living ones. As long as we have a majority, we can make progress. But if I kill the leader or stop the leader, others run out of patience. You can see that these bars are vanishing. It's a random timeout they have. And as soon as somebody loses patience like this one here, he says, oh, we haven't heard from the leader. Elect me. And now he's a new leader. And I can only append stuff here. And this is now done in term 3. Yeah. So I think I've passed the 9 minutes. So therefore, we have to move on to the next topic. But this is a nice thing to play with and to understand what's going on after you have read the raft paper, or just play with it like this. Okay, consensus is nice. Raft seems to be the answer. But obviously, it's not a solution to every problem. If you have a machine system of 100 machines, you want to agree them on the commit of a transaction or on the order of transactions, you certainly don't want to run it through a single raft instance because this would never scale. So it's very good raft, but it's not the solution for all purposes. Anyway, it is used in practical systems. Okay, completely different topic. Just let's jump to something else which is also needed in such a data star, sorting. You would believe that you can read everything about sorting in The Art of Computer Programming from the 70s. And that is true. Unfortunately, nearly all published algorithms, including the ones in The Art of Computer Programming, are completely rubbish on modern hardware. Why is that? Well, what did people do when they analyzed these algorithms? They counted comparisons. They said, how many times do you have to compare two things and maybe swap them to get the whole thing sorted? That was interesting at the time when comparisons were the most expensive thing in sorting. Nowadays it isn't, because nowadays the expensive thing is data movement. Let me give you an example. When I was a kid, I played with an Apple IIe. Yes, I was an Apple fan at some time. However, if I compare the performance of that machine to my laptop today, then the compute power in one core has actually increased by a factor of 20,000. It executes instructions 20,000 times as fast as at the time then. If you look at the time needed for a single memory access, yes, I know at the time it was a byte, now it's 64 byte. Yes, you're right. But the latency for a single access has only become faster by a factor of 40. That is a certain mismatch. And certainly, these days, here this has had one little core with 1 megahertz. But machines today have 32 cores, maybe not this laptop, but others have. And they share the access to the memory. So therefore, if you count this together and take the quotient, you notice that there is a mismatch by a factor of 1280. So getting the data into the processor is actually the problem in sorting now. And if you want to write an algorithm which keeps 32 cores completely busy, you will struggle a bit, and you cannot use nearly any of the published algorithms. So let me tell you how to solve this problem. The answer is merge sort actually works if you do it right. Now, what is the idea behind merge sort? Behind merge sort is the idea you have a huge array to sort. Yeah? You cut it into pieces. You sort the small pieces first. This can be done in parallel, except if they share the memory. Anyway, you sort the small pieces first, and then you merge these by taking, well, you take 2 or more, you take the smallest first into the result, and then the next smallest, and so on. You just follow all these sorted arrays from left to right, and you always put the smallest in here. Now, if you do this naively, this very step here of sorting stuff will be memory bound. Yeah, it's not the comparisons. It is getting the memory into the CPU, which stops you from using all 32 cores. That is the problem. So now what can you do? You use something like a min heap. A min heap is a data structure. You don't have to know the details. It's a balanced binary tree. And the only condition you need is that the things you stick in these little balls have the property that whenever you have a situation where one is the parent of 2 others, then the thing you put here is smaller than the other 2. That's all you need. And in particular, it follows that the top guy here is always the smallest in the whole heap. Now, it turns out that you can insert a new point into such a heap in logarithmic time. So it only takes the number of steps of the height of this tree, not the number of things in the tree, to insert. And also, if you take away the smallest up here, to repair the damage and create a good heap again, also is logarithmic time. Now that's good. So what you do is you essentially take these sorted ranges here and insert them into the heap, such that you can be sure that the top guy is the next one of the result. And then you take them off here. So what is the secret sauce here? Since this heap structure doesn't have to be really, really large, it can fit completely into second-level cache. That means if you come with a new guy up here and insert, all the comparisons, except maybe the first one, will be cache to cache. Yeah, this means that you take a new one. Yes, you have to load a cache line, but maybe you have already loaded one up here. But everything here is in cache. So you can quickly insert, and it's actually fast because the CPU can get the data quickly from second-level cache. And likewise, if you remove something here, yes, you have to write here once, okay. But obviously, this is also just one access per hash line. To repair the damage, you also only compare stuff in here. Everything is in second-level cache, and off you go. That means if you organize this diligently, obviously starting with very small things which you do in another way, which fit into second-level cache already to bootstrap the whole procedure, and then use your multiple cores to make ever larger sorted segments using this technology, essentially everything happens in the second-level cache of your CPUs, and you are fine. Now, towards the end, you obviously have to have some kind of single-threaded work. So the last step has to be carefully done such that it works. But essentially, with this technique, you can sort a huge array which fits in a memory in a way such that all 32 cores are 100% CPU in top. It's possible, it can be done. And that's the end of this story. So if people say they know all about sorting, ask them whether they know this. Next topic. Again, something completely different, which is just in the mixture because it's also used in data stores. Log-structured merge trees. Now, if people have, say, a data store, say, on a single machine first, we are getting to distribute it later. What do they expect? Well, in particular, if you have SSDs, then you probably expect that you can store more data than fits in RAM. Well, it's a data store, so it should probably use your SSD. You would expect that it works well with SSDs and hard disks. You expect that if you do bulk inserts, it's fast. And you probably want to be nearly as fast as you can write data to your SSD. And you expect that if you do reads, and you just hit a hot set, which does fit in memory, then you expect that the data store keeps it in memory and serves it from memory. So that's all reasonable things. But if you look at classical database technology like B trees, they usually fail on at least one of these two things here. Now, they are not so bad with respect to reads and hot sets and so on, but in particular for fast bulk inserts, they usually fail your expectations. Now, log-structured Merx tree is a data structure for on-disk, on SSD, which, well, helps with these problems. Again, I can just give you the idea, and again, other people have worked before me. There's a very nice description in this link, and the link is actually in the slides which are published. Now, that's another one of these things, 3 minutes for a complicated data structure. Let's look at what we have here. We have multiple levels, and you somehow should think of level 0 this level 0 to be in memory. Everything you write to the data store, and we are thinking a sorted key value store here, so we think that the keys are sorted lexicographically or by whatever sort order, and what you want to do is you want to look up ranges and look up key value pairs. And you want to write and delete them, obviously. So everything that is changed in level 0. These arrays here are all sorted, such that you can use binary search to find something in them. So they are built up with some tree structure in memory. So that's fast. You can quickly write, you can quickly take in data, and obviously you do something like write-ahead log for durability. That's solved. Notice that although all of these are sorted, they can overlap. Yeah, so they cover the whole key range essentially. Now, in the other levels, you should think disk or SSD. You should think that these guys are also sorted, but that they are larger. So every level from one to the next is something like 10 times as much data as the one before. Yeah? And what you do, and the other difference is that down here, these do not overlap. So all of the keys in here are smaller than all of the keys here. That is, if you look for something in level 1, you only have to look in one of these ranges. Yeah, likewise with 2 and so on. Now, I've already said you always insert into one of these things in level 0. And if you have enough of these overlapping areas, you do the following. You merge them down to the next level. So what you do is you say you take this one and the key range, and you take all the beginnings of these guys here, do a merge sort, which we have explained just now, do a merge sort, and write out a new version of this incorporating the beginnings of all these guys. Notice that everything on disk is always written linearly, because that is what hard disks and SSDs can do quickly. In particular, hard disks, but also SSDs, they don't like to write something here and here and then here and then here. Then their write performance is very bad. But if you write linearly, then they are fast, because they can use big block sizes and so on. The hard disks don't have to move their heads too much and so on. So therefore, every such merge sort operation pulls this stuff here into memory, maybe in blocks. It does a merge sort operation, writes a new version of this one here, and then discards this one. And in the lower levels, it works the same way. You always merge down to the next level. Now, if you want to overwrite a key, you again just write in the top, and the convention is just if a key is found higher up in this structure, then it's more recent and therefore it counts. If you want to delete something, you write a so-called tombstone. You write this key does no longer exist. So therefore, reading is also quite simple. To read a key in here, what you have to do is you have to look through these things in level 0. If you find it, fine. If you don't find it, you have to go further down, look here in the right area. If you find it, fine. If you don't find it, go further down. If you have fallen through and have not found it, it doesn't exist. So that's nice. Cannot spend more details on writing, but what happens is that everything is written linearly. All files are immutable once written, so therefore writes are fast. Now, unfortunately, if you don't do any more tricks, then reading is now seriously impeded, because it has to look here and look there and look at the other place. And that pretty much sounds like hopping around, and if you have a random read load, then things go badly. So therefore, we need more tricks. Let me quickly summarize what we have before we get to reading. Everything first goes to level 0 mem tables. All files on disk are sorted, immutable. We always merge sort to get from upper levels further down. And obviously, we do compaction. If we notice further down that there was a key and there's another copy of that further up, then the upper one counts, so we can discard the lower one. That's called compaction. All these use sequential I/O. That's fine. Now let's talk about reading. The problem with the reading is that you have to read in various places. In particular, if the key isn't there, you have to look in many places to find out it's not there. Therefore, one uses something called Bloom filters or cuckoo filters, which is again a very nice computer science data structure. And it can do the following. It doesn't use a lot of memory, but it can answer the question, is a certain key in this set or is it not in this set? It's allowed to lie. So if it says yes, then it can lie. But if it says, no, this key isn't in the set, then you are guaranteed that it's right. So, doesn't use much memory. It can lie, but only in one direction. And that's exactly what we need here. Imagine ourselves looking for something here. Well, it's okay in memory. We don't find it. We know if it's in there, it's in here. But that's already too large to keep in memory. So therefore, we put for this immutable file, we compute a Bloom filter, which is much smaller and which we can keep in memory. So therefore, we first ask the Bloom filter, is the key in here? If the Bloom filter says no, we don't have to touch the disk because it's guaranteed not to be there. If the Bloom filter says yes, well, first of all, with very high probability, the key is actually in there. So we actually go ahead, look for the disk, do the seek and get it. And well, if it wasn't there, okay, mistakes happen, it doesn't matter. We have spent a bit of time, but there's no mistake. So it's only Bloom filters or cuckoo filters, the more modern approach, which make this whole thing bearable for random reads. And if you then put the usual block buffering, which basically the operating system already does for you, you get good write throughput and reasonable read performance. That's the story about log-structured merge trees, I can tell here. It's used all over the place. We in ArangoDB use it. So I should admit that I work for a company making ArangoDB. In particular, we use it because we use RocksDB. RocksDB, the storage engine which was developed at Facebook, uses it, but also WiredTiger has a mode for that, so MongoDB is using it, and all these big players all use some kind of log-structured merge tree. It's used all over the place. So it's good. I haven't said it's perfect. We'll see what the future brings. And on to the next one. Again, completely different topic, but it's also used in distributed systems. This is about clocks. Well, you know systems. You know that clocks are out of sync. Well, it's not a big deal if you know how to deal with that. But why is that? First of all, there is general relativity and fundamental problems with syncing clocks, but that's not what we are talking here usually. That's probably a problem for Google with their atomic clocks, but not for us. But in practice, clock skew happens because we don't have access to atomic clocks. And even if we use network time protocol, we have to live with something like 20 milliseconds or so between computers in the same rack or same data center. So why is this a problem? The problem is if we take timestamps on different machines, we cannot compare them. If this timestamp is smaller than that on the other machine, it seems that this event has happened before that, but that might not be true. It might just be a clock running late. So therefore, for all sorts of problems, whenever you want to understand happens after, we are in some kind of serious doo-doo. Imagine we want to study logs of different servers. We want to compare the timestamps to understand what happened when, and well, the timestamps aren't correct. That's a bit of a problem. We want to measure network delays. We want to maybe sort out conflicts arising when we write in different machines. So the problems are all over the place. What can you do about it? We want to implement time to live or whatever. It's a problem. So here again, it's just a very nice idea what to do. If I say logical clocks, then this is some kind of idea where you say, okay, a clock might just be a clock value might just be a number, and I don't care if it doesn't have to do much with reality. That's another concept. This is a mixture between logical clocks and proper clocks. So here's what you do. What you want is that if two events on different machines are somehow linked by causality, so if something happens first and causes something else to happen on the other machine, that is where it is really important that the first timestamp is smaller than the second. That's essentially all you care. If you have completely unrelated events, it doesn't really matter what the timestamp says. So therefore, you identify causality with a message has been sent. Because in a distributed computer system, the only way where something can cause something else on another machine is if there was a network message between them. So therefore, for the moment, we say causality is the same as message. And here's what you do. Every computer has a local clock. And we send a timestamp with every single message sent from server A to server B. That's not a lot of traffic. And whenever we receive a message, we take notice of the largest timestamp we have ever seen. And when a machine wants to read a timestamp of the hybrid logical clock, it simply returns the maximum of its local clock and the largest timestamp it has ever seen. So, if a message is sent from A to B, so imagine some event on server A, it was assigned a timestamp. Then you send a message. With every message, we take a timestamp, send it over, and take notice of it in server B. If this now causes some other event on server B, and we take a timestamp of that as well, then the following happens. The clock on this second system might be late, but since we take the maximum of the local clock and the largest timestamp we have ever seen, we have in particular seen a timestamp which is higher than the timestamp of the event on A. Therefore, the timestamp we take for the second event is larger, and causality is preserved. And the additional benefit is that if there's no events, then eventually, obviously, and no messages, then eventually the local clock will catch up with this largest timestamp ever seen, and we are back to real time. So that's the good compromise. So therefore, causality is preserved, time can catch up with logical time eventually, and therefore it's a good concept. So in a distributed system, you might do something like this. You want to organize transactions or resolve conflicts or whatever. You take these timestamps of hybrid logical clocks. All you have to do is take along with every message, take a timestamp, send it along, and take notice of it at the target. So it's very, very easy to implement, and it gives you a good approximation to this kind of causality you want. Okay, next topic. 10 minutes left. Great. Again, this link has a nice description of what's going on and some proofs and so on, and hints for implementation. That is actually, for a change, not difficult to implement. So that's one of the benefits here. Now, this is the topic I cannot tell you very much about, because it's really the hardest, and it essentially will use all of the stuff I've already talked to you. Now, what is the problem? From a traditional data store on one machine, say a relational database, you are used to have ACID guarantees. So you are used that if you do a transaction, then it happens atomically. So it either happens in its entirety or it doesn't happen at all. You don't have to get a result saying, oh, I've maybe done half of this transaction, but I don't know what I did. Yeah, this doesn't happen. Very good. Therefore, the data store you see is in a consistent state. Every transaction might have happened or not, so you always see a consistent state of the data, which is good. There's another concept of consistency having to do with replication. That is something else here. Transactions are isolated, so different transactions which run concurrently, by which I mean one starts before the other has finished, and vice versa. If they run concurrently, they cannot see each other. And there's various isolation levels. You probably know the SQL standard and stuff. Essentially, the message is concurrent transactions don't see each other. And in particular, you don't see half a transaction being executed. And of course, you want durable, that if the database says, yes, I've written it, you want that it has been written. And if you go back to see if the data is there, the answer is yes, it's there. That is what you want. It's rather obvious. However, in a distributed setting, it's much harder to achieve all this than on a single server. Why is that? First of all, if you have replication, if you have different servers, or even if you just have multiple servers being in the same transactional system, you probably want that they agree on the fact whether this transaction has committed or not yet committed or was aborted. There's no point in having one server believing the transaction is committed and the other not. That would be rather bad. So therefore, you have a problem with atomicity. If your data is distributed, so not everything is stored on every machine and they run raft or whatever to replicate, you probably want to see a consistent state. So you want to ask various machines for the data, and what you expect is that you'll see the result of a certain set of transactions which have committed and not see anything which happened afterwards. That is what I mean by a consistent state. Well, if they can't really agree on things, it's kind of difficult to organize that. Now, isolation is a problem as well. If you have a distributed data store, then you have to do for some transaction, you have to do some changes here, some changes here, some changes there. And you have to make sure that you cannot make sure that they happen at the same time. So therefore, they happen one after another. With these timestamp problems, you probably don't even know when. But still, people expect that the whole transaction is invisible until somebody has decided that it's now committed. So isolation is a problem as well. And durability is a problem because in a distributed system, you live with the fact that a machine can just go. Now, what is your durability worth if some of the data can just go? Nothing. So therefore, you need replication. Yeah, you need to have redundant copies of your data, something which everybody tells you in the first class of data stores and databases don't. Here you have to do it for the simple reason of durability. Then, of course, now you have copies of data. Now the other consistency comes into play. You have to make sure that these copies of your data agree, even if they are written at different times. And isolation is a problem. And then if something goes wrong, you have to organize failover. You have to make sure that the right copy is now read. Maybe you have 3 copies. How do you decide which one is the right one? Anyway, if you think about all these things, then you notice it's actually quite hard. And you slowly get desperate. You see what to do. Can we do this at all? And if you look at what data stores do, hang on, something is wrong here. If you look at what data stores do, very few actually give you proper ACID distributed transactions. If you look at this list here, and I've put a RangoDB here because we don't offer it at this stage. Is there something wrong here? Ah, yes. Thank you very much. So very few actually pull this trick off. maybe the most traditional one is Spanner, Google Spanner, famous paper. They actually pull off distributed transactions with atomic clocks and very tricky things with consensus and timestamps and so on. And more recently, players like CockroachDB, they replicate in an open source way what Spanner did, and FoundationDB, which was vanished for some time but has reappeared now because Apple has first bought it and then open sourced it. And also we have a plan to get there, but it's all a big problem. However, I would say 5 years ago, people would essentially say, well, it's too difficult, don't. Yeah, live with the fact that you don't have ACID in distributed systems, use NoSQL databases which don't give you ACID, and, but the mood is changing. Open source players are offering distributed transactions, maybe not yet with the performance you would like to. There are compromises being made. MongoDB has announced transactions, which is a big change for them. I think they have announced distributed transactions for next year. So slowly people are getting around and saying, well, maybe it's not impossible after all. And I believe it is not impossible. It's just very hard. Anyway, we have a plan to do it. We hopefully get it out before MongoDB. But stay tuned. This will be interesting. Now, it's only 3 minutes I have left, and therefore I definitely won't tell you how to do that. Just to give you an idea, also to somehow put together some of the things we did. One thing which is, to my mind, pretty clear is that a database, any database giving transactions, has to keep multiple copies of your keys, of your data. Why is that? Well, you might have concurrent transactions where one of them has started very early, so it needs to see the old version. But if it's already committed by now, it wasn't committed when the transaction started, but it was committed when another transaction now has started. So rather obviously, you need multiple versions. So that's what's called multiple version concurrency control. So I believe some kind of this you need. You have to keep multiple revisions of your documents or key value pairs. Now, you will have to do writes and replications decentrally because you want to scale out. You want to have multiple machines available. You have to do replication for durability. But you have to do it in a way such that they are not yet visible. And then when the time comes for commit, you have to have some place, and maybe that's a raft ensemble, or maybe multiple ones. There has to be some place, some switch, which really is the truth in your system of this transaction has committed or has not yet committed or was aborted. So one single point of truth you need, or maybe not a single point. Again, it has to be replicated as well. So it has to be persisted, it has to scale out, it cannot be a single raft instance. It has to be replicated because you definitely don't want to lose the information that a transaction was committed. And it has to be resilient for fault tolerance. And so you have to run all these things. And then, of course, you have to implement transaction visibility based on these switches. So whenever you want to see a piece of data, well, there's different versions available. You have to consider all the switches associated with the transactions which wrote these pieces of data, and you have to decide which particular version actually is visible. On the other hand, I believe it can be done. It will come at some performance cost. Hopefully, we can pull it off in a way such that single document operations are still the same speed. We'll see. Anyway, it's a very interesting topic, but I don't have any more time to talk about it. So I stop here. Thank you very much. I don't know whether we have much time for questions, but I will be around to answer questions afterwards. Thanks. And 2 more comments. Obviously, we are hiring 2, and I've put a few T-shirts here. Please help yourself. They are color-coded with the size. Now I'm finished.
Okay, thank you. I think we have time for one question. Is there a question? All right.
Yes.
If in the RAF protocol only a leader is allowed to append, doesn't that in some ways already resolve the drifting clocks on the different machines?
So well, the thing is, the replicas will simply say, I'm not the leader, go away to the leader. Or they forward the request to the leader will write and then replicate. And if you want to have timestamps, you would take the timestamp of the leader. Now, obviously, if the leader changes, you run the risk of the time running backwards. And that is something not even hybrid logical clocks fix for you, because if the leader goes, then you don't know what timestamp to take. Yes, this is a problem, but usually with a replicated log, you are less interested in timestamps, and you are more interested in the sequence of events in the log.
All right. So thanks again, Max.
Okay.